Hello and welcome to my course number 1, electricity, and the subject is Ohm's law. What we're going to do in this course is we will work through the formulas, how we can derive certain values from the formulas. We will solve questions we will raise and will replicate our results in the formula here in real life with the real load and power supply and so on. So I will walk you through how to measure the values, and before we start doing that, we will start with the obvious question. With a power supply, we have a load. We want to know how much power this load requires. We also want to investigate if our power supply is powerful enough to provide the current to the load. We measure all these details here simultaneously. That means we're going to measure voltage, we're going to measure current, we calculate power, and that over time we take measurements here with my precision Keithley 2110 5.5 digital multimeter, and we get support from the additional multimeters I have on the left hand side, for which I can also add calculation into a spreadsheet. So the exercise is constructed in that way that it should be easy for everybody to follow up. After the course, you should all be in a possibility, based on direct current, to calculate the values in your closed circuit and be 100% certain how much power your system requires, how much power you have to deliver, and what load can consume this power. My formula, I defined 12 volt as our power supply. As you can see here, this small battery I have is a micro battery, a deep cycle battery, and this has 12.874 volt. We're gonna monitor that over time when we're connecting the load. We will go also to a deeper, more accurate measurement. We are going into the four-way measurement. That is a two-way, four-way measurement, which gives us higher values. It is good for you to know, because we need to calculate the resistance from the wires as well. They have an influence, and with 4-wire measurement we can exclude this kind of measurement errors. As load, I will use a small 12 volt light bulb. Very important to note, let's just assume I know nothing about my load. In some of the cases that will be the circumstances you have to deal with. So what we have to do is, the first thing is to measure your load. Your load is resistance, and resistance is a factor within Ohm's law for the calculation of power. We see here 2.771 ohm. We take a note of that for the calculation, and we'll see then later on if this calculation does reflect actually the power rating of the light bulb. At the moment I do a 2-wire measurement. I will add now the 4-wire measurement for you as an example to show you the differences in accuracy. Now I have activated the 4-wire measurement. You can see the value 2.745 at the moment. It is set to 4-wire. If I toggle back to the standard value 2-wire, you see 2-wire it measures 2.770, coming back 4-wire 2.741. So it's a small change because the wire is fairly thick, so we have very low resistance in there. However, even this low resistance in the wire can be excluded from the calculation. In higher power factors, or let's say in systems where higher power is required, This is a very crucial point to calculate. Here I have now my setup connected, I have my battery, I have my load, and I'm using the Keesley here to measure both at the same time. I have so-called second display active. That means I display in the first row the current which is required to drive the load. In the second row the voltage. At the moment we have 12.757 volt on the battery. Please note, when we start then with the load, that this voltage will drop, so that has an influence. We have to take that later into consideration. The same counts for the current. Now let's have a look. So the current, you can see the voltage dropping 12.565554. Current is 0.375 ampere, also dropping. I keep it running for a couple of seconds to see if that stabilizes at some point, but it will not. It will continuously drop now in a steady rate, and will maybe hold for a longer period of time at a lower value. We can see that when this value is not changing to a great extent anymore, it holds it on that level. So it slows down slightly. So we have 0.3728 ampere. Good. That's a good value. And we have 12.434 volt. We take both of these values for our configuration and measure that if that reflects based on the load resistance we did measured in our Ohm's law formula for all our values. On my second example, we will use a heating wire. Here that's 1 foot of heating wire. We measure the temperature change when we charge. And we do the same exercise we did with the light bulb, but as you notice with the light bulb, we had a bit of a problem with calculating the current. So what we measured the resistance is the initial current draw. So that is a fraction of a time will be drawn from your household from a battery until it reaches its operating temperature, which is 2,500 or close to 3,000 degrees for Wolfram. And at that level, as you see from the calculation, we had only 34 ohm, and that is the final rating, or the let's say the resistance, which gives us a power rating. So we have here heating wire, a standard heating wire, 1 foot long. So we're going to do the same exercise. We're going to measure the resistance, and then we do all the formula as well, and see what kind of conclusion we can draw out of it. We take our first measurement, and here we do via 4 wire measurement test for accuracy. I measure for this 1 foot heating wire 4.794 ohm at close to 21 degree at the moment. So that is the value we're gonna take a note, and in the next exercise we're gonna use 5 volt from the power supply and gonna drive this load. We measure at 5 volt input power voltage the current which is drawn via the heat wire, and we measure as well the voltage drop, which means this is the amount of energy which can be delivered. So here you will see the current which is delivered and the temperature which will rise. So let's have a look. So 740 milliampere. From this 5 volt only 3.5578 volt is delivered. We have a temperature of currently 80 degree. See when it settles. 3.56 volt delivered. That is a voltage drop which occurs across the load. 3.56, it is stable. We are at 95 degree. Voltage drop stays as it is. Current stays as it is. We are close to 100 degree now. So we're going to take that into our formula for calculation. 100 degree. Now I like to demonstrate to you Kirchhoff's law, second law of voltage, which is about the voltage drop across each resistor or load. Voltage drop has to occur in order to deliver energy. However, voltage drop should not occur in the leads to the load. If there is any resistance between the leads or within the load which is not accounted for the energy dissipation which is required for the load, that has to be marked as a loss. For every design you build, you have to make sure that every component is sound in that point, to that point that energy loss has to be avoided. You do that by measuring your complete circuitry for the lowest loss and for the highest delivery of power. So what do we have here? We have 4 individual different resistors with a bench power supply which will deliver 10 volt, and we measure the voltage drop across each individual resistor. Each resistor or load will drop the voltage accordingly. But what I don't want to see here at the end of that, I don't want to see a voltage drop, because I want to see that the full value of 10 volt is delivered. That's why I use very thick cable, as you can see here, with a 1.5 almost 2 millimeter diameter, to reduce the loss of lines of lead to as much as possible. The Kirchhoff's law does state that each voltage drop added together minus the voltage delivered is equals 0. Very important. Voltage delivered minus the voltage drop added for each resistant is equals to 0. So we have here as a first resistor 10 ohm. They all have a tolerance of 5%. We're going to measure them in detail. 10 ohm here, 15 ohm here, 15 ohm here, 33 ohm here. So we're going to measure then the voltage on each side. We're going to measure the total voltage on here, and we do precise measurement of the individual resistors via 4-wire. Benchmark measurement, which includes the lead wires. So we measure 4-wire test that includes the lead and the resistance, have a total of 73.4040. We take note of that. Now I will go to each individual resistor and we add them now as well. First resistor with 10 ohm measures almost exactly 10 ohm. So that is actually a little bit of lead wire in here, 2.5 centimeter. But this part here, exactly 10 ohm, that's fine. Let's move on to the next part. The next part is a 15 ohm resistor, as we can see, 15.068. So it's also very accurate. So the 5% of tolerance would be much higher than that. Let's go to the next resistor. This one shows a little bit higher, 15.230. Let's go to the last resistor. Resistor is a 33 ohm. As you can see, a little bit less, 32.660 ohm. We take note of that. So we have now all the resistor calculated. That allows us to calculate the power requirement for each load based on 10 volt we deliver. So let's go now through the next stage: voltage delivery, current measurement, and voltage drop from each side, and we take note of that. First measurement will be measured across the resistor, directly coming from the lead to the resistor, and we want to measure the voltage drop based on the 10 volt delivery. And I hope that almost 10 volt will be delivered, so we're going to see how much it's going to be. I'm going to start now. 9.9385 volt is delivered into the system. We have a current requirement of 130 milliampere. So that is our benchmark for how much we can get delivered. We can calculate that later on that amount. Taking the whole resistance we have here, multiply that via this amount, will give us the total delivery of power into the system. That will be a bit less than 10 volts. That's 1.3 watt based on what we see here. This might be a little bit less, 1.28, 1.29. but we're gonna see that. So the next one will be, I go through across each individual resistor and measure the voltage drop, and we take a note. The first voltage drop I measure is across the 10 ohm resistor. I have 1.3621 volt. So we take that down, 10 ohm voltage drop down to 1.3621. We are now across the first 15 ohm resistor. Let's measure that. 2.0527 volt DC. Okay, that's the first 15 ohm resistor. Let's go to the next one. Remember that the next one was a little bit higher in value. Let's see how that pans out. 2.0740 volt. Okay, and let's go now over the last one, the 33 ohm. Okay, now across the 33 ohm. 4.4489 volt. Okay, we're gonna add all these voltages together and see what we come up with. And at the end I would like to measure current correctly. So we had 130 milliampere here displayed on the power supply, and see how that looks like when we measure it via the key sleeve. So we have 0.1346 ampere or 134.6 milliampere. So we're going to take that into consideration for our formula. So we have then now all the accurate values and can now start with calculating Kirchhoff's law, second law of voltage.